a great pleasure to be visiting Korea again, and I thank Professor Chian and Sung-Yoon Kwan for making that possible, and for KAIST for inviting me here today. And I'm going to talk about, well, what the slide said, the Riordan group. As you'll see, many of the examples of the Riordan group go back long before Riordan. The Riordan group paper came out in 1991, so it's coming up for its 20th anniversary next year. If you type in Riordan group in Google, there's over 1 million references. Once you eliminate the ones to the insurance firm and the law firm and various actors, you get down to maybe 100,000. After you cut out a lot of nonsense and duplication, come down to maybe 1,000 references, and once a lot of those are citations, and a number of papers. It was a bibliography that came out 2 years ago, Renzo Sprignoli, and that had 66 references, but I think it's up to maybe 100 now. So, a topic of some importance, and as you'll see, the basic ideas are very, very simple and give you a lot of results in a hurry. It's also true that once you have one individual result, that you can sort of rephrase this so you don't need to use the words Riordan group anymore. Okay, so it's a method of thought. We take two generating functions. G equals 1 plus G1Z. So an arbitrary power series, except that the constant term is 1. And then F, and it has 0 constant term and a non-zero Z term. And then we form a lower triangular matrix. And one thing is worth noting is that it's really convenient to start the indexing at 0, which is a little weird. I mean, this is the 0th column here, but it's worth doing, okay? And so you multiply by F. F has that extra 0 in the front, so that makes the thing triangular. Z squared here. And what you really have is sort of a geometric series of generating functions set up as a lower triangular matrix. Okay. We have the following multiplication rule. So both of these are infinite triangular matrices, and you multiply them together, and the result is again determined by two functions. We let G be the leftmost column and F the multiplier, what we multiply by each time to get to the next column. What color am I using there? It looks like blue. So 1 over G of F bar the compositional inverse of F. And the identity, well, 1 is the generating function for the 1 plus 0 times Z plus 0 times Z squared and so on. Z moves you down. Okay, and what are some examples of the Riordan group? Well, probably the most useful single example is Pascal's matrix. Perhaps we should have called this thing the Pascal group. I don't know. But, I'll explain some of the motivation for the name in a minute. We have the Motzkin triangle for the Motzkin numbers, and the generating function there is m 1 minus z minus the square root of 1 minus 2z minus 3z squared over 2z squared. If we rotate the Motzkin triangle around, we're really talking about a random walk where we start at 0, 0. We can move one to the left, one up, or horizontally. So it's on integer lattice, first octant. And okay, so many of these matrices can be thought of rather directly as random walks with directions imposed. And it turns out this is a key example, because if you do two things, one is put in weights on the various steps. Here the weights are all equal to 1, but if you put in sort of 2 out of 3 arbitrary weights, and then take the inverse matrix, which is you get Favard's theorem, and that leads to a good bit of classical orthogonal polynomial theory. And there's a set of notes by Viennot that explore this connection. Okay. And let me motivate how I got interested in the Riordan group. Riordan was one of the trio, along with Karlitz and Henry Gould, that did old-fashioned combinatorics. In the old days, combinatorics consisted of graph theory, some design theory, and pushing combinatorial identities around. And these guys were geniuses at pushing combinatorial identities around. And Riordan wrote a book on combinatorial identities. And a good bit of it was how sort of classifying them, Chebyshev type, this and that type, and inverting them. And he was a kindly old gentleman and worked for Bell Labs for many years, and then the Rockefeller Graduate Center after he retired from Bell Labs. And the year he passed away was the year that figured out this group structure. So sort of in honor of him, we named it the Riordan group. But such things as Stirling numbers, the first and second kinds, of course, have been around for centuries, along with Pascal's matrix, or Pascal triangle. So the historical roots are much deeper. Okay, but the kind of thing I was interested in was combinatorial identities. And this one's pulled out of concrete mathematics, and moderately complicated. Okay, so we're looking at that top line. What does this thing equal? And step number one is, well, hey, I can see Catalan numbers in there. 1 over k plus 1, 2k, choose k as a Catalan number. Okay. Well, that's a little help, but it doesn't clear things up. So I think the next step that I certainly would have taken was try a small case. See if it's true. See if I've got all the indices right. Okay, we do some routine arithmetic. And it comes out 0. Well, okay. And maybe try another small value. And it comes out 0 again, and at this point we're now ready to make an educated guess as to what the answer is, but you know, being conscientious mathematicians and not physicists, we would like to actually have a proof. And if any physicists here, let me apologize. That's those other guys over in experimental. Okay, that's step one. Try some small cases. Here's step 2. Let's see if we can write this in matrix form. Well, okay, I mean, we had to fill in n equals 0, 1, and 2. And Yeah, we arrange it this way, and sometimes there's a little bit of play. You could put I could have put the minus signs in with the Catalan numbers, whatever. Sometimes you have to write things in reverse order, but okay. That's step 2. Okay. Step 3, we have the parade of generating functions. Okay, and we really have a version of, well, we were putting in binomial coefficients, so the fact that we're getting out sort of every other row of Pascal's triangle with some minus signs stuck in is no big surprise. And we have the generating functions for the columns of Pascal's matrix, so these ingredients aren't too surprising. Times C, and then here's the generating function for the right-hand side. So we've got everything written this way, and if we write that out a little bit more, okay, I've written the Catalan numbers in blue, and you can see, for instance, that 5 is going to multiply by this particular column vector. So we go over and write everything in terms of generating functions. Okay, and does this equal 1? Okay, well, the generating function for the Catalan numbers I think I had it on a previous slide, but okay, we're done with that part. Okay, so well, we factor out 1 over 1 minus z, and then we have the Catalan numbers, but the generating functions become Catalan, instead of c of z, c of minus z over 1 minus z squared. And then we do some arithmetic. Okay. So we reduce this to an algebra problem. And sure enough, things drop out. It's very reassuring to see the 1 pop up at the end, but not a surprise. And we have a proof. We're done. There's only 4 steps. Small cases, matrix form, introduce the generating functions, and do your computation. Okay. Well, this is an element of the Riordan group. Yeah. Okay, and what would it be? Well, the g function would be 1 over 1 minus z, and then what are we multiplying by each time? Minus z and 1 minus z squared would be what we need, yeah. So we have that. Then a couple days ago, when I was working this out, as a nice medium-sized example, said, well, let's lose the minus signs and see what we get. And the answer, large Schroder numbers. And a very similar, the algebra is very similar. I won't bother to show that, and you need to know the generating function for the Schroder numbers, but that's in Sloan's encyclopedia as well as a bunch of books. Okay, and this is sort of sidetrack, but maybe of some interest. Where do Schroder numbers show up? Well, a paper of Ernst Schroder from 1870, looking at 4 different problems in logic, sort of, and one of them is Catalan numbers, another one is Schroder numbers. It's a number of ways you can take n objects and stick in a certain number of paired parentheses. If you put in all the parentheses, you get the Catalan numbers, but if you just put in some of them, you'll end up with this the Schroder number sequence. But here's another place that they show up. Take an n by n board, checkerboard, whatever you want to call it, and actually what you're taking is a permutation matrix. Put a 1 or an x in each, 1 per row, 1 per column. So you have n factorial ways to do this. And then that's stage 1, that's sort of the seed to get everything going. And then any square that's next to two x's gets an x. So it's a cellular automata of sorts with a permutation start to it. And let's look at an example, maybe make that a little clearer.
Do you repeat that process?
Well, let me show you the example. I think that'll. We start by putting one x in each row and column. Okay. And then we say, are there any squares that have two neighbors that are x, and we put x's in there. And then we repeat the process. Now there's two more squares. These two squares have neighbors, two neighbors that have x's, so they get x's. Next stage, we fill in this square and the top square, and then we would fill in these two, then these two, then these two, and the whole board fills up. Okay. Do all the n by n boards fill up? Well, yeah, n equals 1, yeah, it's full already. N equals 2, yeah. N equals 3, takes a little bit of thought, but they all fill up. N equals 4. Well, mostly. But there are two exceptions, and these are the two exceptions. Okay, so we have numbers 1, 2, 6, and 24 minus 2 equals 22. Well, for 5 by 5, I'm not going to draw them all because there's 120 of them, but 90 fill up and 30 don't. And we get the sequence 1, 2, 6, 22, 90, and indeed takes a little work, but that's the Schroder numbers in a automata setting. This was a paper that Brooke Stevens and I wrote many years ago, and he's in computer science at University of Maryland, Baltimore County. And he was able to get a few more values, so we knew, he had a computer program that would check all the values. And yeah, I was sort of surprised. The other surprising results, the number of these sort of permutations that don't grow at all. There's an old paper of Irving Kaplansky from, I think he's still, no, I don't know, he's maybe just died a couple of years ago, active for many years. But he started out, he did a couple of combinatorial papers before he went into algebra and commutative algebra. But using one of his results, able to show that the number of ones that don't grow at all approaches e to the minus 2. The proportion. And okay. Let's look at another example of where the Riordan group shows up. Well, we start with this problem from recreational mathematics. And we have this version of what we might call, Pascal's triangle in many, many variations have been around for centuries. This is one variation. I have no idea who thought about it first. I think I learned about it in Byler's book on mathematical recreations, and that's been out for 90 years or so. And I never would have found it without using Sloan's Encyclopedia of Integer Sequences, and even that, it took quite a search to figure out what was going on. Okay, so we have this rectangle, and we cut it. We look at the sequence 1, 3, 42, 163. And because we're interested in the Riordan group, we rearrange it. Okay. And it turns out that the generating function for the 0th column is b squared over c, where b is the 1 over the square root of 1 minus 4z. b is in central binomial. This is the center of Pascal's triangle if you write the high school version. Well, 2n choose n. And here are the Catalan numbers once again. And really hard to read, but the same, what I just wrote over there. Okay. So we've just created this Riordan group element. Okay, what, if anything, does the sequence b squared over c count? Well, it counts a lot of things. Take an ordered tree, pick a vertex, which you call the mutator, and then count number of points that lie above the mutator. Okay, well, that's a lot of other things as well, but a graduate student in my algebra course, Dev Falara, the first student I've ever had from the country in Nepal, perhaps the first student from Nepal that's ever attended Howard University, I don't know. But okay, look at ordered trees. Same thing as planar trees or plane trees. They're counted by the Catalan numbers, and we mark a vertex, which we will call the mutator. Okay. And we count these. Oops. Yeah, get too tricky. Okay, it turns out that there are 1, 2, and then 6 possible ways to pick a tree, and then pick a mutator. And the next one would be 20. The number of ways to pick a mutator is b, and the basic reason is that the Catalan numbers are if you have a tree with n edges, you'll have n plus 1 vertices. Okay, so this particular fact is quite easy to see. Okay, now let's look at the number of points, including the mutator, that are above the mutator. And here's our sequence again, 1, 3, 11. Okay, so infected, or, I mean, this could be some source of information, and information or disinformation or something's inserted at some point, and then it flows up the tree. You could have a source of, if this is representing a network of rivers, you could have a pollution source, and the pollution would flow. Well, I don't know if it usually would flow upstream, but whatever. The places where it might be the possible sources of the pollution. If the mutator was a test station, you could invent scenarios that make some sense. Okay, so 1, 3, 11. Yeah, if this is the mutator, these are the infected points. The mutator itself is counted. If we go on to the 5 planar tree, 5 ordered trees with 3 edges, I haven't drawn them all out because it would be much too much, but you can see that this, if the mutator is at the base, there'll be 4 infected points. If the mutator is here, 3. So 1, 2, 3, and 4 are the possibilities for this particular tree, and total 10, total 9, 4 if it's the base, 2 if it's the mutator's located here. So you add up the possibilities, indeed it goes to 42. The number on average goes up at a rate of 1/2 of the square root of pi times n. Okay, so you start with this little, I mean, it's just the point here, many points, but one of them is just the Riordan group shows up lots of places naturally, and it's a nice thing to be alert to. Okay. Ordered trees with a uniform up degree. Well, there's ordered trees themselves, even up degree. If the up degree of every point is some even number. If the 0, 1, 2 Motzkin trees, this gives you the Motzkin numbers again, the up degree of every point is either 0, 1, or 2. Complete binary trees, well, then the up degree is either 0 or 2. Incomplete binary trees, well, 0, 1, or 2, but one can be left or right. But you have the same condition at every point. You're not saying we have a little exception here at the root, or that at height 3 that something different happens. So it's uniform. But there's lots of examples. This hex trees we may get a chance to talk about later. Come from putting benzene molecules together in a paper of Harari and Reed of some years ago. So really a graph theory. Okay, so there's lots of examples. You can invent your own set of conditions on up degrees, and you'll get another example, as long as it's uniform. And the key fact here is when you have any of these many classes, is we get the following equation. V equals L times T. Okay. Okay, what is V? Well, it's the T is just the number of trees in your class. Okay. Typically, you know that because you wouldn't be talking about them otherwise. V is the number of vertices. Well, you multiply by n plus 1 for n edges. And one way to do that is multiply T by an extra Z and then take a derivative. Okay. And L is, okay, so V is the generating functions for trees with a marked vertex, which we are now calling the mutator to make it sound biological. L is the generating functions with a marked leaf vertex. So this is a leaf, 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 whatever. And the proof's very simple. Take out a pair of scissors and snip it down. Okay, so what happens? Well, the mutator just became a leaf, so we have the leaf generating function. We have T with a marked vertex, but that's always the root, so it's still just T as a generating function. Multiply them together, you can go backwards and forwards, and you have this beautiful little theorem. And the key for a lot of problems is you really want to know what L is. That's a building block for a lot of things.
It is assumed that the trees are rooted. Is that,
Yeah, ordered trees have a root, yeah, yeah. And an ordered set of subtrees that link to the root, and that essentially is the definition. So you're ranking your subtrees with oldest child, next oldest child, tallest member of the species, next tallest, whatever. So some sort of ordering. Okay, and this gets us to the other part of my talk. Well, they link up. Okay, the uplift concept for ordered trees. Okay, this is essentially just reviewing all the definitions I just had. So what is the uplift principle? Okay, well, of the many classes I just wrote down, the one I'm going to do examples from is ordered trees themselves. Okay, so for ordered trees, okay, the number of ordered trees is the generating function counting the ordered trees is the Catalan generating function. The vertex thing by what we've just shown here is B, and rho is B over C, and by another elementary argument that I'm not going to have time to explain, another useful way for L to be expressed is B plus 1 over 2. So half of the central binomial coefficients. And okay, and this is sort of illustrated. We have 5 trees. So with 3 edges, that's the 5th. The Catalan numbers start 1, 1, 2, 5, 14. So C3 is 5, and here are the 5 of them. There's 20 vertices, and half of them are leaves. Okay. Even that's a little bit of a surprise. Seems like a lot of leaves. Okay. That was a monthly problem not too many years ago. Okay, so let's look at some examples. Okay. The uplift principle says you do things in 2 steps. Figure out what's going on at the root, where it's often much simpler, and then multiply by BC. Multiply by the leaf function. And then you have the result at all vertices. So example number 1. Twig is a vertex with 2 children and no grandchildren. Okay, and beautifully illustrated there in red. Okay. 4 twigs. Okay. 2 children, no grandchildren. No extra children, no grandchildren. Okay. Okay. So we'd like to know what's the generating function for twigs of going over all ordered trees with n edges. In some situations, you might be storing information on leaves. Okay. Never mind. So let's start with the root. Well, okay, we're done. 2 children, no grandchildren, and no way to stick an extra edge anywhere. Okay, well, that's half. We multiply by this, and we get the generating function, z squared times bc, or b plus 1 over 2. And in this particular case, there's no more to do. The number of twigs for trees with n edges is 1/2. And that gets us from, it shifts us from n to n minus 2. And we have this we have this binomial coefficient 2 times n minus 2 over n minus 2. Okay. Plug in n equals 5, see that we've done our arithmetic correctly, and we're expecting 10 twigs, and there they are. When we go any bigger, we'll start getting some trees with more than 1 twig. There are 14 trees, ordered trees, but the other 4 didn't have any twigs. Okay, and let's think about this a little bit more. What's the average number of twigs? Well, this ratio. And as n gets large, n over 32. Okay, and okay, this result surprised me when I first thought about it, I don't know, 3 months ago. What does it mean? It means you add 32 edges to get 1 more twig on average. Well, 32 is a lot of edges. You can make a lot of twigs, you know. But obviously what's happening is that adding edges can destroy old twigs. Somebody suddenly acquires a grandchild, or the 2 children suddenly get 1 more sibling. So, you know, it's okay. Okay, but as I say, it was a little bit of a surprise. Okay, let's look at another application of the uplift principle. Does the average vertex in the average ordered tree have more children or more grandchildren? Well, first guess might be grandchildren, but then we remember half of the vertices are leaves and have no children or grandchildren. So, okay. I mean, this might be a more interesting question in one of those other 8 classes of trees, and see if you could get higher numbers. Okay, but at the root, this is a pretty classical result. Yeah, an interesting argument. Okay. Well, we want here's the root, we want a child. Can there be older children? Well, sure. Don't have to be any, but C could be just 1. But this is the potential generating function. Could your child have children? Well, of course. Could there be younger children? Or more other subtrees? And the answer is yes. So here's our generating function for a child of the root, zc cubed. So that's the step 1. Okay. Well, one result there, though, is that the number of children of the root is 3n over n plus 2. If you go over all trees with n edges, and that rather rapidly approaches 3. So for really big trees, the average number of children of the root is 3. Okay. Okay. And then we multiply by b over c, and the average number of children overall, all vertices, all trees, goes way down to n over n plus 1, so it approaches 1 a little less than 1. Okay, and actually we could think about that. A tree with n edges has n plus 1 vertices. Each of the n plus 1, except the root, is somebody's child. So we could have done this with no machinery whatsoever. Okay. Grandchildren at the root. Well, very similar computations. Actually, there's one tool that I'm using here, and it's not that hard to write down, but if you take the nth coefficient, and this is our nth coefficient operator of c to the m, this equals m 2n plus m over 2n plus m over n. Okay. And the companion if we multiply by b, this comes out. So, yeah, that's the only thing else that I've been using in these computations. Okay, so the average number of grandchildren at the root, 5. Average number of great-grandchildren, incidentally, is 7. Okay. Okay, this is a paper I wrote, I don't know, 15 years ago, called The Higher You Go, the Odder It Gets. The 3 results been known for decades. Okay, and then we do the same thing. We uplift. Once we get multiply by BC, use the same kind of computation, end up with the average of number of children times n minus 1 over n plus 2. And so 2 surprises here. One is that you have fewer grandchildren than children. Second is both limits are approaching 1. Okay. Now to a topic a little more recent. Well, at least I can show you the example. Okay. Okay, we have this some species, and during the summertime it can reproduce, no restrictions. Wintertime, however, it either survives or doesn't survive, but no further production. Okay. Summer comes around, and again, it's unrestricted. Winter maybe survives, maybe doesn't. And summer comes around. So we have this alternation of summer and winter. Okay. So what we have is an ordered tree where the up degree at odd height is either 0 or 1, and we can transform this particular ordered tree into a so-called Dick path. And what we do is we work our way around the tree. I think it's pre-order. There's some computer science term, I don't quite remember what it is. Pre-order transversal. More informally, this is Martin Gardner's article on the Catalan numbers. This was the worm climbing the tree. The term glove bijection has been used. But anyway, we're getting up, down, up, down, up, down, and can read it off as a sequence. And then we can read the sequence using 1, 1 for an up step and 1, -1 for a down step. And we get this Dick path. And, okay, they're all carrying the same information. And let's see, the requirements on our Dick path goes from 0, 0 to 2n, 0, and uses up step and down step, and never goes below the x-axis. And that's immediate from the tree because we can't go below. We always, any edge, we traverse it up before we come back and traverse it down. Okay. And then what we're going to do next is not require the path to finish. It would take partial Dick paths. So Dick paths, but now they can end at any they can end at any non-negative integer. And if we start graphing them, we have no valleys at odd height. Okay, so the first one that we can stick on an up step or a down step. If we add an up step, we move to the right. Down step, we'd move down. And let's see, which one? This is the first one that's forbidden, because this would have a valley at height 1, the low part of the valley, down, up, so yeah. Okay, so we can draw pictures and it all makes good sense. And if we count these a little bit more, we get the following diagram, following matrix. Okay, and a couple things are of interest here. One is that it's not in the Riordan group. For a Riordan group using ordinary generating functions, which is all we're doing today, you would have to have an arithmetic progression. And this is a nice progression, but it's sure not arithmetic. So you know automatically that it's not. Second thing that's interesting is we're getting the Motzkin numbers in the 0th column. Okay, and how would we compute these? Let me line these up carefully. for columns 1, 3, 5, all we do is the old Pascal rule. Just add up what's on the left and what's on the right. So we would then get, if k is odd, this is our recursion. If k is even, however, we can't do that because of these 21, 9 of them came from here and would give us a valley, add odd height. So we don't want the 9, we just want the 12. 2 up steps is fine. Down up gives it a valley at the wrong height. So this is our other recursion. And what we get is an example in something called the double Riordan group. Okay, so what do we need here? We need that G is an even function, F and Z being odd function. Well, we had that in that example. And yeah, so we're going to start with G, and then we multiply by F1. But now we have 2 of these, so we're going to alternate. Multiply by F1, multiply by F2, back to F1. Multiply by F2 again, then F1 again, and so on. So we alternate multiplying by F1 and F2. And it turns out that the combination of that with the even and odd functions works out pretty nicely.
So every second column is going to be a Riordan group, right?
Yes. Right, we can break it down into 2 Riordan group elements. But it turns out that we once again get a group multiplication. And the key to a lot of what we're doing here is this little h function, which is the geometric mean of F1 and F2. Okay. The old identity is still the new identity. Take both of the F1 and F2 to be equal to Z. Okay. Okay, is the Riordan group a subgroup of the double Riordan group? And it would seem at first that, yeah, I mean, just take F both times. But it turns out that the multiplication fails rather quickly on almost any couple of examples you pick. You don't get closure. Can it be fixed? And the answer is yes, and that's where the even and odd restrictions come in. Then you have a version of the fundamental theorem of Riordan arrays. Everything works. The intersection of the Riordan group and the double Riordan group is the checkerboard subgroup, which is exactly this G even and F odd. Why checkerboard? Well, if we put in these restrictions, the matrix looks more or less like this. There are many interesting subgroups of the Riordan group. Okay, and let's talk about one more example. We consider walks from 0, 0 to n0 using up steps, down steps, and level steps of length 2. And we're now going to put on an extra condition. There are no, of these level steps, there are none at odd height. So we start getting these. Yeah. Okay. So no level step. The 10 is the 5 plus 5, not plus the 3. The 5, well, the 21 is 6 plus 5 plus 10. So we have these alternating rules, so it's not a real surprise that we're going to get an alternating generating function. Okay, well, what are we counting here? And it turns out that the 0th column, thanks again to Sloan's encyclopedia, is counting symmetric benzene trees. So we want no 3 benzene molecules to touch each other, and only 1 benzene molecule touching the base. And these are the 5 that are symmetric about the y-axis, if you put the origin in the middle of the base. Okay, and we get these numbers. If we look at the next column, we get all the benzene molecules with these. Okay. I'm illustrating 3 down here. So we have good combinatorial significance for the first 2 columns. And let me finish with a few open problems. Okay. First one is, what in the world is, in terms of putting benzene molecules together? We've got good interpretations for first 2 columns, and I have no idea about the rest of it. Somehow it shouldn't be too hard, but something I'd be glad if you could figure it out. Okay, second problem. That's probably you. Yeah. Okay. We take the even part of the even part of the Catalan generating function. So, okay. Proof combinatorial. There's nothing. It's an easy proof in terms of generating functions. But we take this thing, square it, and we get the Catalan numbers with z replaced by 4z squared. Okay. C, we can do a nice proof using the Riordan group, but I've got no idea what the combinatorics are. With the 5th powers running around, has got a Ramanujan flavor to it. And we're getting alternate Fibonacci numbers here on the right-hand side. So something or other's happening, but I've got a proof and no intuition. Moving on to number 4. Well, we'd like to extend the Riordan group, keep some sort of group multiplication. The one possible next step would be to say, well, how about if we also included the diagonal matrix 1, 2, 3, 4, 5? Is there anything reasonable we could say about that other than it's got to be a subgroup? Okay, then we have the fact that if you take derivatives of these various combinatorial tree kind of functions, that you get m squared times something, a squared times something. And the something's got to have combinatorial interest, and the question would be a good, a good fix on what that is. So it's a little bit of an open-end problem because I'm not saying exactly how, what the candidates are. Any function has a derivative, and you can divide by c squared. There's something there, but I think that would be interesting to isolate what's going on. And I think this is a good stopping place, so let me stop.
Okay, do you have any questions?
Yes.